Hello, welcome to this new approach of teaching due to coronavirus in this subject of engineering economic analysis. Okay, we're gonna dedicate this video to the review of several exercises we're gonna present now. Okay, so welcome to class and let's start with the analysis. Okay, let's see what we have here. We have selected several problems that may be of interest and we'll be glad to apply to you. Okay, we have, let's review this first case. This is quite a simple exercise. We have a person who is selecting materials for roofing his house. Okay, there are he's actually choosing among different alternatives, and there are three alternatives here. The first one is a way of tiling the roof that will have an expected life of 15 years, an annual maintenance of 5, and a price that will be cheaper. This is a cheaper one, although it will have there's a reduction in price against the other, but not a reduction in the install cost, the cost of installation. If we move into quality max singles, we just have the same installing cost, and we have an increase in the quality of the product, and so an increase in the prices. And the annual maintenance will be reduced because the quality of the elements allows this, and the life of the equipment, the expected life, will increase. It will be something like 25 years. Okay, if we just look at the third alternative, this is much more expensive. It's supposed to be made of better materials, more difficult to install, but very low maintenance costs will exist, and the life of the element will be quite long. Okay, how can we handle this problem? How can we deal with this problem? Okay, the first issue that we have to note is that inside this cost, the cost of this element, is clearly the result of the variation of this parameter. Okay, let's clarify. There are three categorical distinctions between projects. The first one is short-term equipment, middle-term equipment, long-term equipment. Obviously, as far as we presume that the house will exist for longer than that, and there's no reason for us to assume that there will be shorter life that may allow restrict the decision to a given amount. Then what we will have to choose is a procedure that will take the whole life of the equipment to be used. Okay, then we have two possibilities. Two alternatives have been proposed. Alternative A. Okay, enlarge. Oh, sorry, capital letters. Enlarge the life of the equipment. This means life of the project equal to, in this case, there is no multiple inside. Okay, we can do the common multiple of all these numbers. It will be 150 years. It comes from 3 times 5 times 5, okay, times 2, okay, 3 times 5 again, so 25 is included, 3 times 5 is included, times 2. Okay, 25 por 50 por 2, 150. Okay, this is one possibility. We're creating an artificial life. We are creating a test, artificial test, where we are supposed to assess the life of the equipment. Another possibility is thinking in terms of using expected or estimate uniform annual cost. Okay. In this case, we're only using cost. We are not matching. We have the price, we have the cost. We have to select the cheapest alternative. Okay. So let's have a look at the process. Using alternative A, what we have is, for the first alternative, mean shingles, okay, for mean shingles, we have for the one project, for one, okay, okay, oh, okay, we get rid of this. We'll just draw first. Let's draw the model. Okay, we have during 15 years, sorry, let's build the arrow. This will respond to 105, 105 payments. Okay, then we'll have 5. Oh, we'll go back to the arrows. During 15 years, let's assume that this is reached here. Okay, this is the temporal axis, and this is 5. Okay, so this is the analysis we have for this case. Okay, so if we now, let's look at this here. We start by assessing what will be the cost, the total cost of this alternative. We will use future value. Okay, sorry, just to be more precise. This is 15 years. Okay. Okay, so let's come here and let's obtain future value of the cost. Okay, at year 15. Okay. First, we have an initial value of 105. 105 is the cost of buy and install. Okay. So future value of this is time equal to 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it is 15 periods after that. So it is F over P. Sorry, I will use here this of 105 times, what is the rate of discount to be applied in this case? 6% is the recommended one, the one that represents this company's decision. Oh, sorry, F5. Okay, and it is 15 years. Now we have transferred this amount into the future. Then we will have the future value of an annuity with a value of 5 and rate of interest 6 and 5, and a number of years is 15. Okay, and then with this expression we will have an equivalent end of the period accumulated cost. This process lasting 15 years will happen 10 times. So now we have to determine what is the, for example, present value, okay, let's be homogeneous, of this total amount during 15 years, during 10 repetitions. To be clear, what we have done here is to substitute all this, okay, by this arrow here. Nothing exists now apart from this, okay. Okay, and this is equal 15. So now we have 10 repeats, 10 repetitions of this amount every 15 years. So what is the present worth of this amount? Okay, the present worth of this alternative, okay, is the result of summing from e equal 1 to 10, sorry, of f, we already know this expression, divided by 1 plus r, up to, and what's up to here? It's 10, sorry, is it is 15 times y. There's a mistake here, it's not 20 but 10. Okay, so this can be computed as a geometric progression. Okay, this will be, here we'll have 1 minus, and the rate will be 1 over, oh sorry, 1 plus r up to 15. The first term will be this one. The last one will be the final value for 10 is now transformed into 11, so 15 after 15 periods, and then we'll have this, okay, f 15 times this expression, okay. Oh, sorry. Okay, now we will operate here, and this will be this term will be okay, minus this one, okay, and then we have this, okay. Then we can eliminate this term, okay, eliminate this term, okay, and the remaining value can also be simplified by okay, we can get rid of this at the next step. Okay, then we eliminate this. We will eliminate this. Well, this here. Okay. Okay. And now we can divide everything by 1 plus r up to 15. Okay. Then this will be reduced to 10. This will be reduced to 1. And this will be reduced to 10. Okay. So this expression will give us the final output. Okay. As you can imagine, this can be quite complicated. We have an easier way of dealing with all this. Let's obtain the present value of, I will follow now this expression, P present worth of alternative initial. Okay, this will be equal to 105 plus P over A of payments 5 0.06 times 15. So per year, this will be constant. Much easier and easy to handle. Less mathematics, less problems. Okay, so let's open Maxima and see what happens. Okay, I will open Maxima. Okay, I will load Ingecon. Okay, then I will ask for this value. Okay, so this is the present worth of the cost of one cycle. Let's transform this. Now we can transform this. Let's call this, for example, K. and let's transform this to an equivalent value. So let's obtain annuity equivalent to a present value. Okay, easy to handle. This is equal to k 0.06 times 15. Okay, and this will be the annual cost of the process. Okay, let's do the mathematics of this. Where k is equal to this value. Let's call this k. Okay, and then now this can be computed. Sorry, this has to be obtained like this. So it is 15.81. Okay, that's a good point. Look, I will switch to a different approach now. Easier to be analyzed. We have an annuity of 5, okay? Oh, sorry, of 15. Let's compute what is the annuity corresponding to this initial payment of 100. If we introduce here the initial 105 installation cost, okay, we have that the annuity of 5 that has to be paid, plus the corresponding, that we have this as the data, plus the corresponding annuity to the initial cost, that is 5 plus this, will directly give us the answer, 1581. The equivalent annuity to this will be 1581. And charging annually this 1581 forever will represent this alternative. We don't need to play this game with the simulation of the 100 years. So now the problem is easier to handle. We can come here, annual cost, and the annual cost is 15.8. The annual cost of this will be the annual cost of this will represent 3 of annual maintenance plus the annuity equivalent to 140 during 25 years. So let's do the example. Sorry, for the name is Quality Max Singles. Let's keep the formulas there. Quality Max Singles has an annual cost of 3 plus the present, the annuity corresponding to a present value of 140, 6%, 25 years. Okay, this is annual cost 1. We can add here, okay, this is annual cost 2. Notice that I have obtained it now in one single step. 3 is the annuity equivalent. Okay, this is the annuity, this term, and this is the annuity equivalent to 140, that is the initial installation cost. Let's take this formula, let's come into Maxima, and let Maxima do the arithmetics for you. Just remember to switch this and to simplify this. 1395 is the percent cost. Okay, so we can now see that there is a reduction in cost here. Okay, let's see what happens here. The annual maintenance is 1, 50 years, and 220. Okay, oh, I don't remember the name. Let me copy the name of Quality Metal Roofing. Okay, then the annual cost is simpler. Just come here and cost, so 3 is equal to 1 got value for upper annuity, and then the annuity corresponding to 204, I think, of 0.06 during 50 years. Let me check if the numbers are okay. 220, sorry, not 40. And this is the annuity for this case. Again, as maxima, how to get it. $14.95. Let's write the result here. 95. So that means 14.95. Okay. So this is now the ranking. The best alternative is clearly this one, the one in green. Okay. This will be the permanent cost during 50 years or during 150 years. This will be the permanent cost during 150 years, and this will be the permanent cost per year during 150 years. So in any case, the best solution is the one in the middle, as usual. Okay. So now compare all this expression that may be full of problems for you to calculate to this simple solution that is just with one single line of code you solve the problem. Let's save the work, and we'll go into the next, in the next video we'll go into the next exercise.